Hello everyone, welcome back. This is the second chapter, Structure of Atom. So in this chapter we'll go through the findings in trying to establish how an atom looks like. We'll try to do justice in understanding the underlying principles regarding the structure of an atom. And this chapter is itself important because it's where all the small details, the fundamentals of understanding the subject chemistry, even physics as a whole, all the fundamentals, the underlying principles are included in this chapter. So I suggest you pay attention to this chapter. Now, to start with, and we know Dalton's atomic theory, where John Dalton, he proposed that all matter are composed of small particles, indivisible particles called atoms. Now we know that the atoms can be further divided into subatomic particles, starting from electrons, protons, neutrons to quarks. And the early developments, the early idea of the electrical nature of matter was provided by Michael Faraday in his experiment. His observation was that whenever we pass electricity through a solution of an electrolyte, then due to electrolysis, he found out matter gets deposited at the electrode. So that is, he gave the idea of the relationship between electricity and matter. Now, J.J. Thomson, by the end of 19th century, using discharge tube experiments, he discovered electrons. Now, this is how discharge tube looks like, a glass discharge tube. Now, what they did was J.J. Thomson. They pumped out all the air. This is to vacuum, the vacuum pump, and then they supplied a high voltage close to the range of 10,000 volts. And then in that experiment, they found out that the tube started to glow, and it seems the glow migrates from the cathode towards the anode. So that's why Thomson referred to as the cathode rays. And later on, they found out the cathode rays were negatively charged because it seems the rays were emerging from the cathode side, that is the negative terminal. So that's how they could Thomson in his experiment found out. Now the cathode rays, the nature of the cathode rays were like, if you place an object on this side, suppose any object, then it casts shadows. And then it also, they were invisible unless you put some phosphorescence or fluorescence material, then it starts to glow. Otherwise they were invisible particles. And then if they also showed mechanical effects, like if there is a simple tool or pulley which can rotate, then due to these rays, the toy or the instrument used to rotate, so it also showed mechanical effect. And then this rays showed magnetic and electrical behavior. That means they were deflected. Suppose if you supply external current, suppose negative charge, then they were deflected. or if you apply magnetic effects, then they were drawn. The rays were drawn towards those magnetic plates, and so on. Those were some of the observations made by Thomson regarding the cathode rays. Now, with the idea of this cathode rays, Thomson found out the value of a charge to mass ratio. That he calculated the charge to mass ratio E/m, and he calculated it to be around 1.75820 into 10 raised to the power 11 coulombs per kg. And Robert Millikan, in his oil drop experiment, could calculate or could determine the value of charge of an electron, and the charge of that electron from Millikan's oil drop experiment, charge of an electron was found to be 1.6022 into 10 raised to the power negative 19 coulombs. Now, with this, we can determine the mass of an electron. So the mass of an electron would be given by E/E/m. So if you put these two values, E/m and then the E value, then approximately we'll get 9.1 into 10 raised to the power minus 31 kg. This is the mass of an electron as calculated from charge to mass ratio and the charge of an electron. Now, Goldstein, 1886, after Thomson's discovery of the cathode rays, that means the negatively charged particles, Goldstein, he, using the same build-up, the same experiment, but here in this experiment the only thing was that he used perforated, or he made holes in the cathode terminal. So, and then he performed the same experiment, and in his experiment, in Goldstein experiment, he found out that the area towards the cathode side, it glowed. It gave a red glow. That means if the negatively charged particles were migrating from the cathode side, then if there is a red glow, this suggests that there must be another type of ray coming from the anode towards the cathode side and making this the portion behind the cathode terminal to glow. So he termed that as the anode rays, because the rays seems to emerge from the anode terminal, and these anode rays were called as the protons, or positively charged, and the cathode rays were called as the electrons, or the negatively charged particles. The properties of anode rays are similar to that of cathode rays. They also shows the mechanical effect, electrical and magnetic effects. Then they have mechanical effects as well. They cause shadows and so on. Both of the rays, they travel in straight lines. So except that one is positively charged, anode rays, and the other one is negatively charged, the cathode rays. That's the difference. Now, after the discovery of protons and neutrons, protons and electrons, there was an anomaly in determining the mass of an atom, except for hydrogen, where the mass of proton and the mass of electron adds up to the mass of the hydrogen atom. Except for hydrogen atom, the rest of the atoms showed anomaly. That means they were short. The mass of the rest of the elements were, when you put together the mass of protons and electrons, it doesn't add up to the actual mass. Therefore, Chadwick, he performed another experiment through which he discovered another particle. Now, his experiment was that he bombarded beryllium, thin sheet of beryllium with alpha particle. So Chadwick, he bombarded a thin sheet of beryllium with an alpha particle. This is the helium atom. This is the alpha particle. So when he bombarded the beryllium thin sheet with helium atom, the alpha particle, then he got carbon atom and a slow moving particle, which now it's known as the neutron, or neutrally charged neutron, or neutrally charged particles. We know that the cathode rays were the negatively charged particles, or the electrons, and the protons were the positively charged particles. And now another entity, a neutron, was discovered by Chadwick through his experiment. Now, with the discovery of this neutral particle, the mass of an atom, the anomaly was sorted out, because this neutron was almost the same, it has almost the same weight as that of a proton. So when you add all those particles, then it gave the actual mass of an atom. That's how the mass of atom was sorted out, by discovering the fundamental particles. So as you can see, here is a table of the particles, the name of the particles with their symbol, mass, charge, and their discoverer. Now, this has been provided in your readout, so you go through the readouts. Electron, it's represented by a beta, or -1 e, and then 0, and then the mass 9.1 into 10⁻³ -31 kgs. It was discovered by Thomson, Stoney, Lawrence, 1887. Then the proton, it's denoted by this H1, because proton, in a hydrogen atom consists of one electron and one proton. So if you take away the electron, it leaves you just with the proton. So we use the symbol H1 as proton, because once you take out the electron, it's left with only the proton. Therefore, we use this as the symbol. It was discovered by Goldstein and Rutherford, 1907. And then the neutron, we write it as this. The symbol is this, N, 1 and 0. And then it's neutral in charge. See, the charge of an electron and a proton, it's almost similar. And it is negatively charged. This is positively charged. But neutron is neutral charge. And then it was discovered by James Chadwick, 1932. And if I'm not mistaken, these Goldstein and Chadwick Goldstein was the student of Thomson, and Chadwick was the student of Goldstein, if I'm not mistaken, or Rutherford. I think Rutherford, if I'm not mistaken, something like that. So you can refer to the readout that I've provided you. Okay, now the fundamental particles that make up the atom, from those experiments we know that electrons, protons and neutrons are part of atom. But how are they arranged inside an atom, or how they build up the structure of an atom? So there were some atomic models that were put forth by different scientists, and the first attempt was done by Thomson himself, J.J. Thomson. And his model is often referred to as the budding model, because he suggested that in a sea of positive charges, means all these are positive charges, the negative or the electrons were embedded inside. That's what he proposed in his model of atom, which of course was not true. And later on we know about Rutherford's experiment, Rutherford's cold foil experiment. Rutherford in his cold foil experiment, he found out that almost the maximum portion of the atom is empty, and there was a dense area, or an area which is so concentrated, because the alpha rays that he used were reflected in the same direction. So, and some were reflected by a larger angle, some were reflected by a smaller angle, and so on. So from his experiment he found out that there was a large concentrated area inside the atom, and he referred to that as the nucleus. And now we know that the nucleus is where both the protons and the neutrons, they occupy the area, the nucleus of the atom. Now if you think, the analogy is like, if the size of the atom is, if you think about the size of an atom as a stadium, a football stadium, then the nucleus will be a grain of sand inside the football stadium. That is how compact the nucleus is. It's very small, and almost all the atom is empty. I mean, around, people say it's 99% of the atom is empty. Rutherford, from his experiment, he proposed that since the nucleus is concentrated and it is positively charged, because the alpha particles, which are also positive, gets reflected. So and we know that the protons are the positively charged particles. So he suggested that the protons and the neutrons reside inside the nucleus, protons and neutrons, and the negatively charged electrons were revolving around them. That's what he proposed. But there were some drawbacks because of his proposal, of his theory, so of his model of the atom. Because according to Maxwell, any charged particle, which is rotating around a charged particle, and if they are oppositely charged and they attract each other, suppose in his because Rutherford's model, the electrons were revolving, which were negatively charged, were revolving around a positively charged nucleus. Therefore, according to Maxwell, that negatively charged electron will be attracted by the proton, by the nucleus. So it'll spiral. The electrons will go inside the nucleus itself, so that will result in the collapse of the atom. And therefore, that was a major hindrance in establishing the structure of the atom. Now, so 10 game, or the model of atom that we use today, it was put forth by Niels David Bohr, or often called the Bohr's model of atom. Bohr's model of atom, or the quantum model of atom. That's what we'll learn. But before we move on to Bohr's model of atom, let's discuss some of the properties of charge. That the first property is that charge is always quantized. That means we cannot have fractional charges, number of charges. It is whole numbers. They are whole numbers, quantized. And then we know that the charges can be positive, can be positive or negative. They can be positively charged or negatively charged, as we have seen, electrons and protons. And then the charges is scalar, not vector. Doesn't have direction. It just have the magnitude, and that magnitude is 1 over 4 pi epsilon naught q1 q2 over r squared. If the two charges are separated by a distance of r, then the force, the magnitude of force, is given by this equation. So those are some of the properties of charge. And let's move on to the atomic number, mass number. Suppose if X is the symbol of the element, then we usually denote the atomic number on the bottom by Z, and the mass number A on top of the element. Suppose for hydrogen we write 1 and 1, because atomic number of hydrogen is 1, and the mass of hydrogen is also approximately close to 1. Suppose for sodium we have the atomic number is 11 and the mass number around 22 or 23 I think. Yeah, and that's how we represent. And this mass number, so we'll start with atomic number. Atomic number is equal to the total number of protons present in the atom, or it's also equal to the total number of electrons of that particular atom. When it comes to mass number, the mass number is equal to the sum of these two. Sum of total number of protons, and number of neutrons. So that gives us the mass number of the element. Now there are some definitions like isotopes, isobars, isotones, and isoelectronic. This will be given in your printout, in your readout, but you need to keep track of these definitions. So we know that isotopes are elements having the same atomic number but different mass number. Same atomic number but different mass number. And then isobars means same mass number but different atomic number. And then isotones are atoms of different elements which contain the same number of neutrons. Isotones are those which contains different elements, but they have the same number of neutrons, so they are called isotones. And isoelectronic means different atoms with the same number of electrons. Suppose oxygen and fluorine, they have the same number of electrons as suppose the sodium, and so on. Though these are some examples of isoelectrons or isoelectronic atoms.